of the session we can discuss that. Fine.
Okay. Yes, ma'am.
Okay, so the streaming has started. Let's quickly look at the topics of week 2 and then we will move on to week 3. All right. Okay. So in week 2, what are all the topics you have seen? Do you remember? So week 1 itself we started determinants, and in week 2 we have continued the properties of determinants, right? You have seen several different properties of determinant, and you might also have seen one important thing about determinant, like based on the different row operation how the determinant will vary, right? So several things you might have seen about determinants, right? Okay. So uh, also you might have seen what is mean by inverse of a matrix, right? Can you tell me what is the relationship between determinant and inverse of a matrix?
Adjoint table data, ma'am.
Understand my question? So maybe I can, okay, you have given the formula, that's also fine, but my question, maybe I'll put it in this way. Under what condition on the determinant will the inverse of a matrix exist?
If determinant is not equal to 0.
Determinant is not
Yes,
equal to
ma'am.
0.
Determinant is not equal to 0.
Determinant is not 0.
Okay, this is a very important criteria which you all should remember. Okay, so when determinant is non-zero, only in that case the matrix will be invertible. So this is for square matrices. Of course, we are talking about determinants. All right, and maybe you have seen, you must have seen these so different ways of finding solutions. So you have seen that this Cramer's rule works only when you have a square matrix and that matrix is invertible, right? So one,
But if determinant is non-zero, it doesn't imply that it will be invertible.
yes, it will imply that it is invertible. If determinant,
Always.
yes, always. It's an if and only if condition. So if you
Okay.
have an n by n matrix, then determinant of A is non-zero if and only if A is invertible. Okay, this is an if and only if condition. Okay. Okay, so this
Okay.
Cramer's rule, you might have seen, this works only when you have an n by n invertible matrix, right? So this is how you might have done. So for example, if this is a 3 by 3 matrix, then you remove any ith row and replace it with the constant vector, right? And then you find the determinant of that and divide by the determinant of the original matrix. So by this way, you obtain x1, x2, x3. Okay. Fine. So why for this Cramer's rule we will get only one x1, x2, x3? Can anyone tell? So you are having a system Ax is equal to B. Now for this system, you know that the system may or may not be consistent, and even if it is consistent, it may or may not have unique solution. Here we see that we are having only one solution. It means we are having a unique solution. Can you tell me the reason for that?
Determinant is non-zero.
Determinant is not 0.
Because determinant is not equal to 0.
Yes, yes. So when determinant is non-zero, the system will have a unique solution, right? Okay, fine. So here, this is the formula for the inverse of a matrix, right? And using inverse also, once you know that you can find the inverse of a matrix, you can also so use this method of finding the inverse and just multiplying A inverse to B to get the values of x1, x2, xn. So this is the second method, right? And then the next method is the Gaussian elimination method, for which you don't need any restriction on your matrix. It can be any rectangular matrix. Okay, even if it is square, it need not be invertible. Okay, so there is no restriction on the matrix. So for any matrix, Gaussian elimination is applicable. So for Gaussian elimination, you must first know what is a row echelon form and a reduced row echelon form, right? And then what is row echelon form and reduced row echelon form? There are no doubts in these topics, right?
No,
Yes,
ma'am.
no doubt.
Okay, fine. Oh, so then from reduced row echelon form, RREF form, so you can find what are
Ma'am,
yes.
that can you tell that, ma'am? Row reduced echelon form.
See, row echelon form means For example, if you're, for example, let's say you are having, maybe let's take this matrix. Okay, so this matrix, what is the first non-zero entry of each row?
1.
1.
1 1.
And what about the 0 row? Does it occur at the last? Always see for
Yes,
this
ma'am.
here, always the 0 rows occur at the last. Okay, so the first point is that first of all, any row should start with the non-zero number, which is 1. Okay, any non-zero row, the first non-zero element should be only 1 and it cannot be anything different from 1. Okay, and in the next row, if there is any other one, then it should appear only to the right of the previous one. You see here, so this one appears only to the right, this one appears only to the right, it cannot appear below it. Okay, so it should always appear to the right. This is the second condition. The third condition is that if there is any 0 row, then it should appear at the last. Okay, so these are the three conditions for row echelon form. Okay, and reduced row echelon form, all these three things are needed. In addition to that, for any non-zero row, the leading entry in the row is the only non-zero entry in its column. It means what? So let us take any leading entry in the row is the only non-zero entry in its column. Take any column. Okay, so this is now, what is the leading entry here? Can you tell me which columns contain leading entry?
1.
First column and second.
First column
First column
and third column.
And third column.
Third column.
Okay, so now in this column, okay, so in this column, apart from this leading entry, are there any other non-zero entries?
No, ma'am.
No. What about this? Again, this
First
and
and
this
second
are
column.
the- right?
Ma'am, is always leading entries considered as 1?
That is the first condition I told. So for a row echelon form, the first non-zero element in each row is called the leading entry, and that should be 1. Okay, that is the first condition.
Yes, ma'am.
Alright? Okay. And then here you see in all the cases, these are the leading entries. And whenever there is a leading entry, you see that apart from the leading entry, there are no other non-zero elements in that particular column. Okay?
It doesn't matter in the first row if it is the first element is not 1. Any entry it is leading should be 1. That is the condition, right?
Correct, correct. For example, here you see that.
Yeah, that's why I asked.
Yeah. Okay, fine. And here you see that these are the leading entries. And these columns do not contain any other non-zero rows. So all these matrices are in RREF form. Okay. Now maybe I will give you another example. Tell me whether it is in RREF form or not. Is this in RREF form?
No, ma'am.
No.
No.
Is this
Because last column.
okay? Is this in REF form?
Yes.
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 Yes, ma'am, it is.
Okay. So this is REF, but not RREF. Right? Okay. What about this matrix?
It is
Yes.
REF. It is RR. It is REF and not
REF.
RREF.
Okay. Okay.
Yes, in both.
But be careful. It is REF fine, but RREF, are you sure?
No, ma'am,
Not
it is not
RREF.
It
Not
is
RREF.
not RREF because see, this is a leading entry and it contains a non-zero element apart from this. So again, this is not RREF. Okay.
Ma'am, but the same condition, ma'am, the one which you put in the right, 1, 2, 0. In that one, the second column is having 2, right? It is not having 1, right? So still it is RREF.
See, the thing you should understand is that now this is a leading entry and this is a leading entry. You should look at the columns which contain the leading entry, not all the columns.
Okay.
Okay, fine. Okay, so why maybe just one more
So
example.
first one is RREF.
No, it's not RREF.
Ma'am, there
Because
is
here is a 1, right? If it is 0, then it is RREF. See, for any column containing a leading entry, that column should have only the leading entry as the non-zero element. There should not be any other non-zero element.
Okay, column wise only we need to be confirmed.
Yes. Clear? Okay.
Yeah, clear. Thank you.
Okay, fine.
So, ma'am, we can say like RREF matrix are always be a scalar matrix.
No, for example, here you see this matrix. Is this a scalar matrix?
No.
No, right? Okay. Got it?
Yeah. Mhm.
Okay. So also you can have rectangular matrices also in RREF form, not necessarily square matrices. So here, for example, you take this one, 1 0 1 0 0 1. Is this RREF or REF?
REF.
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 This is REF, but not RREF.
RREF.
Okay. And suppose I am having 1 0 2 0 1 3. Now
REF. It is
RREF,
in
ma'am.
both
And
REF or
REF.
RREF.
both, right?
Then how it becomes RREF?
Because now again the same thing. Just look at the leading entries. The columns containing the leading entries are not having any other non-zero entries apart from the leading entries. That's all.
Okay. Okay.
Here? Okay.
Yes.
So, ma'am, it's true like for every RREF matrix, they are REF.
Yes. Because RREF matrix includes the conditions of REF.
Yes, ma'am.
Okay. Fine. Okay, so continuing. So what are dependent and independent variables? So here you see that what is a dependent variable? A column containing a leading entry. So you have, this is the first column, second column, third column. Okay. Now which columns are containing the leading entry?
First and third.
First one.
First and third.
Right. So if this is the case, then you have x1 and x3 to be the dependent variable, and the independent variable is the column that does not contain any leading entry. So here it is x2. Okay. Can you tell the same for this? So this is column 1 2 3. Tell me which are the dependent variable and which are the independent variable.
Dependent.
1 and 2 are dependent.
Independent. Independent x3.
X2 and x3 is independent. Right. The same, can you tell here?
2 and 3 are dependent or 1 or
x2,
independent.
x3.
So you
Independent
should
to
tell it
x1.
in terms of variables. Remember that, okay?
Yeah.
Because we are here considering the equation Ax is equal to B. So here x is nothing but x1, x2, x3. Okay, fine. So here independent variable is x1. Now here
X1, X2 is a dependent.
X1, X2.
X1 and
independent
X2 are
x3.
independent. Yes, ma'am.
so here x3, correct. All right. Okay, so the next thing is what is Gaussian elimination method. Okay, so first thing is that you are having a system of linear equation in the matrix form Ax is equal to B. Then how to find the solutions for this system using Gaussian elimination method? The first step is that you write the augmented matrix form. What is augmented matrix form? So you write the matrix A and attach this vector B to this matrix A and call this new matrix as the augmented matrix. Okay. Then you perform elementary row operations on AB. What are the elementary row operations? These are the elementary row operations, right? So these are, I guess, probably from week 1, right? So you perform the elementary row operations, right? And then convert this matrix to RREF form. Okay. So once you convert it to RREF form, the new matrix which you obtain is, we give the name RC. Okay. Now you consider this system Rx is equal to C instead of Ax is equal to B. Now this Rx is equal to C is a much simpler system of equation. So it is very easy to solve. Okay, because you see it is only like an upper triangular matrix. Okay, so it is an upper triangular matrix, and here all the entries are 0. So very easy to solve the systems here. Okay, so we find the solution of this system, and the good thing is that this solving the simpler system will give you the solution of the original system Ax is equal to B. Okay, so what are the steps for Gaussian elimination? find the augmented matrix, reduce it to RREF form, okay, and the RREF form of the matrix, you call it RC. You find the solution of the system Rx equal to C. That will give you the solution of the original system Ax is equal to B. Okay, fine. So here, I just wanted a quick example. I have given the main steps here. So you are having this system here. Okay. So for this system, what is the size of this matrix A? Can you tell quickly?
3 by 4.
This is a
3 by 4.
Okay. Now here I have given the augmented matrix, and also I have given you. So this is your matrix RC. Okay. So now from this, can you tell me what are the equations for Rx is equal to C?
X1 is equal to 1. X2 is equal to 1.
X3
X3 plus X4 equals to 1. X3 plus X4 equal to 1.
Okay. So here, what are the dependent and independent variables?
X4 is
X1
X1
and
is
X2
independent.
are dependent.
Here X4 is independent and all three are dependent.
X1, X2,
X2.
X3 are
Dependent.
Dependent.
and X4 is
X4 is a independent.
okay. So here X1, X2, the values are already there. For finding the value of X3, you just put some value for X4 and find the value for X3. So X3,
Ma'am,
yes.
excuse me, a small doubt, ma'am. X4 is also a dependent, right, ma'am? Because there is only one leading entry, right, ma'am? One.
The fourth column, where is the leading entry in the fourth column?
In the last row, ma'am.
What is mean by leading entry? That should be the first non-zero entry of the row. So for this row, is this the first non-zero entry?
Oh. No, ma'am. Okay.
Okay.
Ma'am, just one follow-up question.
Yes.
This is the in the last row and the last column is the one, and above that, suppose one above that is one also. That means it is a leading or non-leading.
This
So-
is not. This is not leading anyway. Here is a leading entry. I want to ask whether it is REF or RREF, right?
Yeah, yes, ma'am. Yes.
It will be still in RREF form because here you don't have any leading entries. The problem will be only when there are any non-zero entries in this part.
Okay, ma'am. Yeah.
Okay. Okay. So here, how do you write the solution for this system? So the solution for this system is nothing but
X1 comma
1 comma 1 comma. So suppose you call the X4 is independent, so it can take any
T.
value K.
Okay. Yeah, okay.
Okay.
1
So-
minus K.
Yeah. Where K is an element in R. I should write that. Otherwise, it is incomplete. Where K is in R. Okay. So in this scenario, how many solutions do you see?
Infinite.
Yeah. So you see that you have infinitely many solutions.
Ma'am,
Okay.
small doubt. How can you say that it is infinitely many solutions?
Here you see K is in R. So in R, how many elements are there?
Real numbers. Okay. Yes, ma'am.
So that many values you can put here and you will get that many solutions for the system, right?
Yes,
Okay.
ma'am.
Okay.
Ma'am, in
Yes.
case suppose X4 is not independent, in that situation it will be unique.
Yes, the existence of independent variable only will give you infinitely many solution because this independent variable is going to contribute for this variable constant here. Okay.
Yes,
So
yes.
you see variable scalar here. That is why you are getting infinitely many solutions. So independent variable only if it is there, then only you will have infinitely many solution. If there are no independent variables, then you will get unique solution. Okay.
Ma'am, it is restricted to the RREF form, right?
We are doing Gaussian elimination. So here we are doing RREF form. What's your question?
I don't know, ma'am. The independent scenario basically.
Yes,
So it will be applicable only in RREF form matrices, right?
we are defining dependent variable and independent variable from RREF form. Yes.
Yes, ma'am. Okay. So in the RREF form, we have any independent variable, then we can say that matrix have infinite solution.
Yes, yes.
Okay, ma'am. Okay, thank you.
Ma'am, that means if there is no independent variable, that means it will have unique solution.
Exactly. If you people are having this as a question, maybe I'll write it here. So, existence of independent variable implies the system has infinitely many solution. Okay, and this is if and only if, in fact, and if there are no independent variable, the system will have a unique solution. The system will have unique solution. The system will have unique solution. All right. Fine.
Ma'am, what in case of no solution? When
No solution. Okay, so
yes,
no solution means what will happen? When will you get no solution?
basically when the generally one of the element in the B will be 0 and it will not be matching to any of the equation on the left hand side, right?
I guess that is some condition which was given right before introducing this dependent and independent variable. I have not mentioned it here. Since you asked, maybe I can tell it to you.
Okay.
Where is the space to tell it? Maybe I'll tell it here. Okay. So, what is the assumption we are having when we are doing this dependent and independent variable is that, so when you are finding the RREF form, okay, in the RREF form of the matrix, okay, so you see that suppose there is a 0 row here, okay, suppose you are having, so in R there is a 0 row, okay, but the corresponding entry of C is non-zero. Then in that scenario, you will see that Rx is equal to C will have no solution. Why? Why is that so? For example, let's say you are having some matrix like this.
It won't match.
Yes. So here you see that x1, x2, x3. Okay. And here just x1 is 2 minus 3 and 1, suppose I'm having. Then what is that you get? X1 is equal to 2. X2 is equal to minus 3. And this side 0 is equal to 1. You see the problem here?
Yes, ma'am.
Okay. So whenever this kind of a scenario arises, in that scenario, you will have no solution.
Ma'am, one more question, ma'am. If there is no solution, then the determinant should be 0. Is that right statement, or that is
No,
not?
not necessarily. See, determinant 0 may still have a infinitely many solution case. Okay, so determinant non-zero will guarantee that unique solution will exist. But determinant 0 may have either infinitely many solution or no solution. Both the scenario may happen.
Okay, okay, thank you.
Fine. Okay.
Ma'am, in the above case, that is the only possible way that Rx equal to C is a no solution, basically, right?
Yes, usually this is the scenario, or the other way around also can happen. Maybe you have a 1 here and a 0 here. That scenario is also there. Okay, so you have,
Yeah, scenario will be the same.
yeah, similar scenario.
Okay,
Okay,
ma'am.
only in those scenarios you have no solution. Yeah.
Yes, ma'am.
Please open that slide where you write the note.
If we have multiple independent variable in the same scenario which we explained, suppose the last two columns are independent variables, then we will consider as K.
No, no. In that case, you will not consider both as K1, K2.
Okay, okay.
Okay, fine.
Okay, ma'am. Okay.
So finally, we are now moving to week 3 topics. Okay, fine. So what are the things we have seen in week 1 and week 2? So week 1, we introduced what are vectors, and then we introduced what are matrices, right? And then we saw some various properties of matrices, right? And then we saw various techniques to solve system of linear equations. So what is, these are kind of preliminary things we have prepared for studying vector spaces. Okay, so what is the motivation for vector spaces? So you consider the system Ax is equal to B, where A is any rectangular matrix. Okay, so we have seen there are few ways like Cramer's rule, using inverse or Gaussian elimination to find the solutions of the system. Okay, so now let us look at this set, which is X is set for X in Rn, where Ax is equal to 0. What do you call Ax is equal to 0, the system?
Homogeneous.
Homogeneous.
So this S is nothing but the solutions of all the homogeneous system. Okay. So now S is a set of all solutions of the system Ax is equal to 0. Okay. So now what do you know about this set S? What is the element which is always there in S? S is always
Real number.
S is always this. We are talking about a set.
In the homogeneous, it will be 0.
S is always non-empty, and what is the vector it always contains?
Rn.
0.
The 0 vector, right? 0 vector is always there in this set, right? So S is either a, what are the two scenarios for S? S is either singleton set.
Or non-empty.
No, it is not non-empty. That is what I already. Okay, fine. You are saying non-empty is
Or
fine.
it contains 0 vector.
It can see 0 vector is the case of singleton, or it contains infinitely many. Infinitely many elements. Okay, fine. So these are the basic things about S. Okay, so now what is more we can observe about S? Let us assume that S is an infinite set. What we can see, there are two elements, then V1 plus V2 is in S, right? So what is that? So V1 is in S means you have a V1. V1 is in S means a V1 is equal to 0. And V2 is in S means a V2 equal to 0, right? Now from this, what can we say about V1 plus V2? AV1 plus AV2 is equal to AV1 plus AV2. So this is 0 and this is 0. So you get this is 0. So this means V1 plus V2 is also in S. So this means this set is closed under addition, right? Closed under addition means what? So if you take any two elements, then the sum of those elements will also be in that set. That is what is meant by closed under addition. Now let us look about closed under scalar multiplication. It means what? You take any vector and do the scalar multiplication of the vector, then that vector also will belong to the same set. How is that possible? So it's very simple again. So V1 belongs to S means you have a V1 is equal to 0. Now what about a times of alpha V1? It is, yes.
So in the above one, basically V1 and V2 will be 0 only, right? 0 vectors only, right?
No. Why they should be 0? I have considered this case when S is an infinite set.
Okay.
Okay, so for example, this can be, okay, here it is not 1, 1, 1. Maybe let us say here some other matrix is there. Okay, so there this need not be a infinitely many solution case. Okay.
Okay.
Sorry, not a unique solution case. So here I am considering a case when there are infinitely many solutions. Okay. So for maybe for matrices with non-zero determinant, okay. So you can see that maybe I can give some specific examples when we look at
yes, that would be better.
Null spaces. Null spaces, when we see, I will give you several examples where you can get infinite set for that. Okay, fine.
Ma'am, sorry, ma'am. If you, the first one you said yes is either singleton, ma'am. So if you the statement which you are making singleton means it is having at least one element. That's why you are calling that as a
Not
single.
at least one element, exactly one element, and which is 0.
Okay, okay,
Okay, fine.
okay.
Fine. Here we are.
Ma'am,
Yeah.
singleton, it will contain only zeroth, like the one element only, and which is zero only, ma'am.
Yes. Yes.
So except zero, it can't accept any entry like one or two.
See what happens in the unique solution case. What happens in the unique solution case?
So unique solution means this is the only solution, and that could be anything, ma'am. But it would be unique.
Yes. But see, always 0 is there in S. Yes or no?
Okay, yes, ma'am. Yeah, yeah.
See,
It's a x equal to zero
I'll
scenario.
tell you,
Yes.
Ax is equal to 0. Let us say A is an n by n matrix and A is invertible. Okay.
Yes, ma'am.
Now,
Then every x will be 0, right, ma'am?
yes, A inverse Ax is equal to 0 implies x is equal to 0. So, only possibility here is x is 0. Otherwise, it cannot be 0.
Okay, ma'am. Yes.
Okay,
Fine?
okay.
Okay.
Yes, ma'am. Yes, ma'am. It's good. Yeah.
Fine. So, here you see that A times of alpha V1 is equal to alpha AV1 and AV1 is equal to 0. Right? So, it means alpha V1 is also in the set S. It means what? It is this set S is closed under scalar multiplication. Okay, fine. So there are several sets like this for which you can see the set is having this property that it is closed under vector addition and scalar multiplication. So for example, look at this set, check whether it is closed under addition. How will you check whether it is closed under addition? You take two elements from the set. What about the sum? Is it also there in the set?
Yes, ma'am.
Yes, x1 plus x2 comma
Yes,
6.
ma'am.
Right?
It would be
So the
behave like
sum is
the original set.
okay.
Behave
Now
like
what about the scalar multiplication?
alpha x comma 0.
Yes, ma'am.
Yeah,
It is
it would be
also.
by multiplication, but that would be belong to the original matrix.
Yeah. So both are closed under. So under both operations, it is closed. Closed under addition as well as scalar multiplication. Right? Okay.
What is that term means closed, ma'am? We can simply say that it's a vector addition or vector multiplication.
See, what is mean by closed? That's what I told you. Take two elements. If the addition, sum of the vectors is also inside this set S, then we call this set
Mhm.
to be closed under addition. Okay.
Okay.
Closed means whenever you add two vectors, that vector will not go outside the set. It will stay inside the set. So that set is closed under this addition. Got it?
Okay, ma'am. Okay. Yes, ma'am. Yes, ma'am. Perfect.
Now look at this set. Now check whether it is closed under addition. Take two entries from this set. Now what is the sum of this?
X1 plus X2, comma Y1 plus Y2,
Y2 plus
comma
2. No, ma'am, it is not because 2 is not. Only.
Yes. Now you see that this is not in S. So this is not closed under addition. What about closed under scalar multiplication?
Same thing, ma'am, because of 2.
Right? So for example, if you multiply with maybe 2, then you will get 2x comma 2y comma 2. So this element is not in S. So this is not closed under scalar multiplication also. All right? Okay. What about this set here?
S contains only 0.
Sorry?
The set S contains only, okay, here xy1, right?
Yeah.
Okay.
Okay. What about this set S here? X set of all x plus y is equal to 1.
Ma'am,
It
in the above,
won't comes under addition, but it comes under multiplication.
Okay, let's check that. Someone else was also asking something, I guess.
yes, ma'am, in the above one, when you multiply the scalar,
Mm-hmm.
so basically all the elements are changing here, right? Which do not belong to a set S. 2x, 2y as well as
That
2y.
is not a problem. See, 2x is still in R, 2y is still in R. So x and y, the first part and second part should be in R. That is all we want. But the
Okay.
last part should be 1.
Should
This
be.
is where the problem comes, not here.
Okay, okay, okay.
Fine. Okay. So here, for this set, we will check closed under vector addition. So here you have x comma y, where x plus y is equal to 1. So let us pick two vectors, x1, y1 and x2, y2, such that x1 plus y1 is equal to 1, x2 plus y2 is also equal to 1. Now let us add them up and see what is happening. So x1 plus x2 comma y1 plus y2 is this entry. Now what is x1 plus x2 plus y1 plus y2? It is nothing but we can rearrange.
Yeah, 2 ma'am.
Yeah, so x1 plus y1 and x2 plus y2, which is 1 plus 1, 2. Right? So it means what? This sum is not in S. Right? So it is not closed under vector addition. What about scalar multiplication?
Ma'am, if sum
will be
comes
there.
to 1, suppose sum
Because
comes
it
to
will
1,
still be
then
1.
it will be closed under vector.
Yes, for if it is equal to 1, then it is closed under addition.
Because of x plus y equal to 1.
Yes, yes.
Because it should be like the original behavior basically.
Yeah,
The
that is,
S matrix. Yeah.
yeah. So because of that condition, the vector will still be inside the set. Hence, it will be closed under addition. Okay. So whatever condition is here, if the sum also satisfy the condition, then that vector will be that set will be closed under vector addition. Okay.
Can we check by putting the values of y1 and y2 as 1 minus x1 and 1 minus x2?
Sorry, what?
Can we check by putting the values of y1 and y2? It's like 1 minus x1 and 1 minus x2.
See, if it satisfies for one example, it does not hold. But if it does not satisfy for one case, then you can say that it is not closed under addition. Do you understand what I'm saying? Suppose you are getting one specific case where the sum is still in the S. That will not prove closed under vector addition. You have to prove vector addition for any two general vector. But counter example, if you are providing with one vector, then that is enough to say it is not closed under vector addition. Do you understand? Yes?
Okay. Yes.
Okay.
Ma'am, just one question for
Yeah.
conclusion. If a vector is comes from a space, that vector must satisfy the condition. If it satisfies, then it will be come from a space, sample space.
Sorry, you are asking that suppose you are having two vectors and if the sum is also from this set S, then it is closed under addition.
No, if condition is satisfied, then it will be.
Yes, if the whatever condition is there, if that is satisfied, it means the vector belongs to the set S.
It means for set problem, for general, from A to C, if we generalize this statement, that means if condition is satisfied, it will belongs to a set. Otherwise not.
Yes, yes.
Okay, thank you.
Okay. So closed under scalar multiplication. How to check closed under scalar multiplication? Let us take a vector x comma y for which x plus y is equal to 1. Okay. Now let us multiply with alpha. Okay. Or maybe you can take any specific number also. Maybe you take 2 or minus 1 or anything. Okay. So now what happens to 2x comma 2y? So what is the sum of these two? 2x plus 2y? It is 2 times of x plus y, which is 2, which is not 1. It means what? This 2 times of x comma y does not belong to S. Okay, so it is not closed under scalar multiplication.
So at all times, ma'am, it should retain the property, right? And the condition, basically.
Yes, yes. Okay, fine. Now this problem I'm giving it as a homework, but just to tell me from guess whether it is closed under addition and scalar multiplication or not. What is your guess?
Yeah.
No, ma'am.
Yes, ma'am, it is.
No,
Yes,
and
ma'am.
for scalar it is yes.
Closed under vector.
So plus z equal to 0. Addition.
You will get the answer by the end of the session. Those who remember, you can check the answer at the end of the session. Okay, you will get the answer by the end of the session, but not directly. Maybe indirectly you will get it. Okay, fine.
There is so much suspense, ma'am. You are creating here.
I am giving you time to think. I'm not creating any suspense at all. I'm just giving you time to think and also space to listen to the class properly, so that you will get some answer for this somewhere, right? You will wait for it. Okay, fine.
Ma'am, in the first one, there is r square, and the last one is r cube, right? So what that imply?
See, r, we don't call it r square and r cube. We say r2, r3. Okay, so here we are having only two ways. So these are all Euclidean spaces, we generally say. So here Rn is usually Euclidean space. Rn means you have n components. R2 means only 2. R3 means 3. That's all.
Oh, okay. Okay, okay.
Okay, fine. Okay, fine. So here we just saw that if vector addition and scalar multiplication separately, here it is combined. So v1, v2 are in S, then alpha 1 v1 plus alpha 2 v2 is also in S. Okay, so where a1, a2 are real numbers. So if both it is closed under addition and scalar multiplication, so we can combine and get this, right? Do you see how we got this? See, v1 belongs to S, so we know that a1 v1 belongs to S. v2 belongs to S, so we know that a2 v2 belongs to S according to scalar multiplication. Since we are assuming both vector addition and scalar multiplication, so I am assuming that S is closed under addition and scalar multiplication. Okay, so I'm assuming this. Then you know that this property is because of scalar multiplication. Then because of vector addition, I know that a1 v1 plus a2 v2 will also belong to S. This is because vector addition. So you see that if these two are there, then we can straight away write that this is also in S. Okay, and this is called a linear combination of these vectors v1 and v2. Okay, so this is scalar multiplication, this is vector addition, and now together whatever we get here is called a linear combination of v1 and v2. Okay, suppose we have more number of vectors, then you consider a1 v1 plus a2 v2 plus etc an vn, then this is a linear combination of the vectors v1 v2 vn, where this a1 a2 an are all scalars. Okay, so what is linear combination, I will tell you again. For before that, here are few more things to start introducing vector spaces. So here you see that some sets are following this behavior and some set are not following this behavior. Okay, so what is happening then? So we saw this one important set here. It is satisfying this property that it is closed under addition and scalar multiplication, right? So what is happening? Okay, so there are few more things also we should look in a set to form all the main properties required for a vector space. Okay, so roughly we can think of a vector space V as a collection of objects that behave similar to vectors in the set S. Okay, so how it should behave? It should be closed under addition. It should be closed under scalar multiplication. Okay, first of all, we should be able to perform two operations, which is vector addition. We can add elements. Okay, and we should multiply scalars to the elements of V. Okay, and these operations should satisfy few conditions, which we call the axioms for a vector space. Okay, so what is the first thing we see? That for a vector space, addition should be defined for the vectors and scalar multiplication should be defined for the vectors. Okay, should define for the elements of that, and then it should be closed under addition and closed under scalar multiplication. Okay, fine. Then what? So naturally, what are the properties we see in R2? We will see first. Okay, what are the naturally occurring properties in R2? Let us observe. Okay, so what is the vector v1? Can you tell me?
It's a 1, 2, ma'am.
What is v2?
2, 1.
2, 1.
What is v3?
1,
Minus
1.
1, 1.
Okay, fine. Okay, now v1 is 1, 2. v2 is 2, 1. v3 is minus 1, 1. Okay, what is v1 plus v2 now?
3, 3.
3, 3.
What is v2 plus v1?
3, 3.
Same. 3.
Okay, you see that v1 plus v2 is same as v2 plus v1. Okay, so if you change the positions also, the addition is still same.
Closed.
The value is
Closed.
still the same. So then we say that addition is commutative. Commutative means when we shift their positions and the value does not change, then that property is called commutative property. Okay.
Ma'am, this is same like closed under addition also, right?
See, closed under addition, what does that mean? You take any two vectors from a set, and if the sum of the vectors are also in the set, then that is called closed under addition. Here we are talking something different. You
Okay.
change the position of the vectors and add, then the sum will remain the same. That is called commutativity. Okay, so addition is commutative here. Okay.
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay, now associative. Any other questions? Okay. So what is associative property here? Now what is V1 plus V2? We have already calculated, which is 3 comma 3. Now what is V3 minus 1 comma 1? Now what is the sum here?
2, 3, 4.
4.
Okay. Now let us change the brackets. First we will just write V1 and then we will add V2 plus V3 now. What is V2 plus V3?
1 comma 2.
1 comma 2.
Now the sum is still 2 comma 4, right? So if we change the brackets also, if the values still remain the same, then we say that addition is associative. Okay. Now the next thing is that, now let V be any vector in R2. Can you find a vector such that when it is added to V, the sum is still V? So V is any vector in R2. So let us say V is any x comma y. What is the vector you can add to this so that it will still remain V?
0, 0.
0, comma 0.
Right? So you have the origin here. Okay. So that origin is called the additive identity. Okay. So it means what? If you add any vector to this identity, it will give back the same vector. Okay. This is called additive identity. And now what is additive inverse? Find a vector such that when it is added to V, the sum is the zero vector.
Minus of that vector.
Minus V.
Minus V, right?
Yes, ma'am.
Okay. So here you see that this is called the additive inverse.
Ma'am, in this case, every V would be every minus V would be unique, right, ma'am? For every vector.
Yes. Okay.
Yes, ma'am.
Fine. Now, what is the same question comes to scalar multiplication now. Find a scalar such that when it is multiplied to V, the new vector is still V.
1.
Yes. Okay. And this is the identity of scalar multiplication. Okay. Fine. Associativity for scalar multiplication. So now also we are just doing the bracket changing. You know that the answer is 6V1 in both the cases, right? Okay. Fine. What is distributive property here? Suppose let us say you have 2 times of V1 plus V2. V1 plus V2 was 3 comma 3 if I remember correctly. The answer is 6 comma 6. Now what is 2V1?
2, 4.
2, 4. And what is 2V2? V2 was 2 comma 1. So 2V1 is 4 comma 2. So the answer is still 6 comma 6. So you see that 2 times of V1 plus V2 is 2V1 plus 2V2. Okay. And the same we are doing now to distribution of scalar multiplication with respect to vector addition here. No, scalar addition only. Because here I am doing the addition of the scalars. Okay. So here 5 times of V1. And here 2 times of V1 plus 3 times of V1. It is, you know that here it is V1 was 1 comma 2, right? Or what was that? 1 comma 2. So it is 5 comma 10. Now here what is 2 times of 1 comma 2 plus 3 times of 1 comma 2? 2 comma 4 plus 3 comma 6, which is 5 comma 10. So the value still remains the same. Okay. So what are the properties we have observed for the basic space R2? You see that for R2, first of all, we have vector addition and scalar multiplication is defined. We have seen vector addition and scalar multiplication in week 1. Do you remember?
Yes, ma'am.
And we know that for R2, the operation is closed. If you add, it will still be in R2. If you scalar multiply, it will still be in R2. So they are closed. And then we just saw with some example, and also you can generally prove also that all these properties are true for any vector in R2. All these 8 properties, which are called axioms. Okay, we call it axioms. So now
Ma'am, could you once repeat the first statement?
this one?
No, above. Yeah,
Yeah.
yes.
So now we take the example v equal to R2. For R2, we have already defined vector addition and already defined scalar multiplication, and both are closed for this set. So vector addition is also closed and scalar multiplication is also closed. It means what? If you add 2 vectors in R2, you will get another vector in R2. And if you do scalar multiplication of a vector, you will still be in R2. So in R2, vector addition and scalar multiplication is closed. Next, we have all the 8 properties here, and
Ma'am,
these 8 properties, yeah.
Yeah, one question from Axiom 1.
Yeah.
Here, ma'am, we are just changing the position V1 and V2.
Exactly.
Not inside the content, means X coordinate or Y coordinate.
See, the position is changed means the vector itself is changing, right? So here, what is happening? 1, 2 plus 2, 1. Here, we are doing 2, 1 plus 1, 2. Okay?
Okay.
So we are just shifting the vectors here.
Ma'am, the example is such that it looks like that we are changing the position of x and y within the vector, which is not the case.
No. So I should write it like this maybe.
Yep.
Right? Now it is clear, I hope. So V1 plus V2, this is V1, this is V2.
Yep.
So now you get 3, 3.
3,
And
3.
here, this is V2 and this is V1. So maybe if you want a different example, I can take another vector u and show you. So maybe let us take, what is this vector? Can you tell me?
Minus
3, minus 2.
Minus 3, minus 2.
Minus 2.
Okay. Now let us call this as your V1 plus U. Now what is V1 plus U, you see? What is V1 plus U?
4,
4, 0.
4, 0.
4, 0.
Yes.
Now what about U plus V1? So U is 3, minus
3,
2. Right?
minus 2.
So now it is again 4, 0. Okay.
I mean, vector space, we cannot see the difference between these two.
See, earlier the people were thinking that we are just shifting the positions of the vector itself. That was not the case. That's why I gave a different example.
Yes, ma'am. We are actually shifting the content inside
The vector itself.
Yeah.
I mean, it is just theoretical. In graph, we cannot see any difference.
See that, yes, you are having V1 and then we are taking V2. So if you are looking first V2 and then V1, then you have the second case. That's all. Nothing big here. Okay.
Yes, sir.
If we see the position respectively to the each of the vector, ma'am, then it would be different basically. Then it would be meaningful. Addition is a commutative. Otherwise, in the graphical method, it will be fixed position. And then
Yes.
we are just adding.
Yes. See, this addition commutativity, maybe in this case, it is very trivial case. See, we are starting with a very trivial case to give the motivation for you. What I'm trying to do here, let me tell you. I have taken some very simple sets where the vector space properties are there. So instead of just giving you the definition of vector space, I am giving you some very basic set where we can see all the properties which are given in the list of vector space definition. Okay, so that it is easier to understand and also get a motivation why these conditions are there in a vector space. Because for very basic sets, all these properties are there, and from these basic sets only bigger sets are evolving, right? So if these properties we can see in basic set, and that is formed as all the condition criteria here. You see what is a vector space definition? You have a vector addition, you have a scalar multiplication. Okay, so this first tells you that you take any vector v1 from here, any element v2 from here, you add them up, and the vector will be still inside v. Okay, similarly, you take any scalar from here and an element from here, do the dot scalar multiplication, that will be still inside v. So here the first one is saying closure under addition, and the second one is saying closure under
Scalar.
scalar multiplication. Okay,
Ma'am,
yes.
and why don't we have division and subtraction?
Division, see, subtraction of course obviously comes, but division is something different. So here we are doing only scalar multiplication. Okay, so automatically if alpha, you know that for real numbers, if alpha is there, then 1 by alpha is also there for non-zero alphas. That is all automatically coming, so you don't have to define separately. The same comes for subtraction also, because you have addition and also scalar multiplication. So let us say you have v1 plus v2 is defined, alpha times of v is defined. Okay, now I am going to multiply -1 to v2. Okay, now what is this vector? This is nothing but minus v2. Now I can add v1 and minus v2. This is nothing but subtraction. So automatically these things will come from this basic operations. So this is sufficient to give you this subtraction operation, and division means you are going to just multiply with 1 by alpha whenever alpha non-zero. That's all, right? So there is nothing to define separately here. That is why we have not defined them. Okay?
Okay, ma'am.
Fine. Okay, so the first thing what we are doing for vector spaces, we are first saying that the set should be closed under addition and closed under scalar multiplication. Next, we are saying that all the 8 properties which we saw above, closed, this addition is commutative, okay, associative, okay, and then existence of additive identity, existence of additive inverse, okay, then identity for scalar multiplication, associativity for scalar multiplication, and then distributive properties for scalar multiplication. If all these properties are satisfied for a set, then we call that set to be a vector space. Okay, you understand?
All 8 property, ma'am.
Yes, all 8 property together with this closure under addition and closure under scalar multiplication. See, usually in regular course, how I was taught at least was that they simply start with the definition of a vector space. They write all these things and tell us, give us few sets, tell us to verify whether these properties are satisfied, which I found it very vague. So that's why I started with the properties first with some simple sets. Okay, now you know what are this property, what is the meaning of these properties. So if a set is having all these properties, then such a set is a vector space. So you understand?
Yes, ma'am.
Okay.
Yes.
Fine. Okay, so now here are few things which you should know when you are verifying a vector space. To prove that a set is a vector space, we need to verify additive and multiplicative closure. Here by multiplicative, I mean a scalar multiplication. Okay, and all other axioms given above. So you have 10 conditions, you can say, including addition and scalar multiplication closure. You have 10 conditions. Okay, if all the conditions are satisfied, then only you can say a set is a vector space. If just one of the vector space axiom fails to hold, then V is not a vector space. Even if just one property fails, then it cannot be a vector space. Okay, so we have already seen one example where all these 10 things are satisfied. What is the space?
R square, R vector space.
R2, right? We saw the case R2. So the example, can you take some simple examples for R3 and also visualize the same properties for R3 also? Yes or no?
Yes, ma'am.
Yes.
So you can do for any Rn, in fact.
Yep.
Yes.
Yes, right? So you can say that Rn with usual addition and scalar multiplication, that is the very first example you should all remember for a vector space. Okay?
Ma'am,
Yes.
this R2, R3, these all are vector spaces, and these are kind of defined like
a two-dimensional space and three-dimensional space. So with the n number of dimensions that we include the all, I mean higher dimensions, 4D, 360, 7D, all.
N means it can take any natural number. So whatever is your n, yes, it takes that dimension.
So, but the vector spaces could be like this Cartesian plane is a vector space. This 3D environment in which we are,
Yes,
it's
a
also
vector
vector
space
space.
can have dimension 5, 6, 7, and so on. Okay.
Higher dimensions don't have the complexity to handle. I mean, they have a lot of complexity now.
See, vectors dimension 100,000, anything will happen. In fact, R2, R3 are not going to help you. Only vector spaces of higher dimension is what is you are going to work with, because in a data set, if you take any vector, what is the size of a vector? You take any data set, you have handled data sets, I hope. What are the sizes of each data you are having? Take any row or column. How many elements are there in a row or column? Do you see just 2 or 3? You see so many, right? 20, 30, any number can be there in a row or column, right? So these rows and columns are representing your vectors, correct? In a data set, right?
Yes, ma'am.
So in reality, you are going to deal with Rn, where n is some huge number.
Means we cannot imagine the physical dimension like that.
See, we are
2D,
just
3D.
getting an idea and getting some intuition from R2 and R3. R2 and R3 is only for intuition and understanding the concepts for a bigger dimensional space, because we cannot visualize beyond that. Okay.
Ma'am, can we represent zero vector space of zero dimension as R0?
Usually we don't have any such notation, only the zero vector. Zero, see what is mean by zero itself, it is maybe considered as a subspace of a set, but it alone as a vector space, that is very, very, I have not seen, at least just the
Ma'am,
zero.
it is said.
See,
But ma'am, it is.
we don't consider it as a vector space, maybe it as a subspace we can consider, but it has no dimension. If you just consider zero, it does not have any dimension.
Ma'am, I guess it is a point size vector space.
Yeah, it is just a point, right? So there is no dimension. So at least one dimension means you should have the real number, you should have at least a line, right?
Okay, ma'am.
Fine. Okay. So yeah. So if just one of the vector space axiom fails to hold, then V is not a vector space. Okay. So 0 element 0 belongs to V of a vector space V is always unique. There cannot be more than one 0 element for a vector space. Okay. And the real number 0 in R and the 0 vector of a vector space commonly denoted by the same symbol 0. For example, so I'm saying that 0 times of V is equal to 0. What does this mean? What is this 0 and what is this 0? V is a vector in R2, let us say. 0 is a scalar. Now what is this 0 and what is this 0?
Left side it is scalar and right side it is vector.
Yes. So on the left hand side, this is a real number, right? And this is an element in R2. So this means that it is
0,
0. Okay. So you should remember, you should understand from the context what the 0 means. Okay. That is the statement given here. From the context, you should understand what the 0 means. Okay. Okay, it is standard to suppress this dot. So usually for the scalar multiplication, we don't write this dot always straight away. We just write AU. Okay, fine. And every element of a vector space is a vector. That's all. Okay, and the very first example, of course, is Rn. Remember, here Rn, we are talking about usual addition. Usual in the sense component-wise addition and scalar multiplication. Okay. Fine. Because why I am saying is that you can define addition and scalar multiplication in a different way also, not necessarily component wise. You can define it differently also. We will see examples. Okay, please wait. Okay, and
Ma'am,
yes.
Ma'am, just can you just scroll a bit, ma'am? The place we have written 10, 10, 10. Ma'am, just below, just below. It was just beside notes. Below that, you have written 10. specifically a number 10.
Oh, this one.
Yeah, ma'am. What is that, ma'am?
Oh, I'm talking about 10 conditions here. 10
Ma'am,
conditions are there for a vector space, including so you have 8 axioms,
yeah.
additive and additive closure, scalar multiplicative closure. So 1, 2, and then plus 8. So 10 conditions are there for a vector space. All 10 conditions should be satisfied for a vector space.
Okay, ma'am. Thank you, ma'am.
Yeah. Okay. The set of all m by n matrices with real entries. So this forms a vector space. For example, I'll just write it for the 2 by 2 case. So 2 by 2 matrices means, let us say, the set of all A, B, C, D, where your A, B, C, D are real numbers. So this forms a vector space. You can check that all the 10 conditions are satisfied for this set. Okay, so this is a vector space. And this was the first set we saw today, the solutions of the homogeneous system. This is a vector space. This forms a vector space. Okay, we will come to this note later on. Okay, so this is a vector space. Okay. Now, let us look at this example where your V is same, but
Ma'am,
your...
a small doubt. Could you repeat about the matrix?
This
Yeah.
one?
Yes, ma'am.
The set of all m by n matrices, all the m by n matrices, if you take, you have to take only one specific size of matrix. M and n are fixed. So if you consider all the collection of that matrices, that will form a vector space. So for one example, I have considered the set of all 2 by 2 matrices. So it means what? How it is closed under addition. You take any 2 by 2 matrix. Is the sum is also 2 by 2?
Yes, ma'am.
Okay.
Okay,
Yes.
okay. Okay, it's talking about the order of the matrix, right? You're
Yes.
considering as the vector space.
Yes. So here,
Okay.
all these matrices together will form a vector space, and you can check each of these properties separately for this set here. Okay. Fine.
Got it, ma'am.
Okay. Okay. Now we are looking at the same R2, but here we are defining scalar addition differently, not the usual scalar addition. Usual scalar addition here, what should come?
Plus.
Plus. Now here, if I am defining it to be minus, then this is not this may or may not be a vector space. There are cases where it may be a vector space when you are defining differently. Sometimes it may not be vector space. So in this case, do you think it is closed under addition?
No, ma'am.
See, the difference of two real numbers, is it still a real number or not?
Yes.
Yes.
Yes, ma'am, it is.
It is.
Closed under addition, right? Yes or no?
Yes, ma'am.
Yes.
Shall we do an example and then we'll try to see that one? That
See,
would be
there is nothing to see much. See, take any two real numbers, 2 and 3. When you take the difference, it is another real number. So this is still in R, right?
okay.
X2 is in R, Y2 is in R. X2 minus Y2 is still in R.
Yes, yes.
So this element
Just
is in R2.
Yes, yes, ma'am.
So this is closed under addition. Also, this is the usual scalar multiplication. So you know that this is also closed under scalar multiplication.
Yes.
Right? Now, what
Yes.
about the very first property, addition? Is it commutative or not? Let us check that. Okay. So now already you are given, let us call this as your, so this is your first vector and this is the second vector. So let us call this maybe u and this is v. Okay. So now u plus v is given to you. This is your u plus v. Now let us try to find what is v plus u. So v plus u is y1 comma y2 plus x1 comma x2, which is, for the first element, it should be
X1,
usual addition.
X1, yeah. And Y2 minus X2, which is not equal.
Yes. So you can see that
It fails.
x2 minus y2 is not equal to y2 minus x2. So u plus v is not equal to v plus u. So this is addition is not commutative. Okay. Fine.
How minus is here? How? Any
How?
minus, y2 minus x2? How?
That is how we are defining addition here. For these second components, You have to subtract. That is how we are defining addition here.
Okay, ma'am. Okay.
Fine.
Second component. Where's
Fine.
yes, ma'am.
Let's
Thank
move
you.
to the next one. Okay. Fine. Consider the set V is equal to set of all x comma 1, x in R. The addition and scalar multiplication on V is defined as follows. So here x comma 1 plus y comma 1 is x plus y comma 1, and c times of x comma 1 is cx comma 1. So here we are going to check whether it is a vector space or not. We don't know whether it is a vector space. First, are they closed under addition? You take two vectors.
Yes, ma'am.
The sum is also in V. Yes?
Belongs to R, yes.
They both belong to vector space. Sorry,
The set.
addition and multiplication.
Yeah. So for multiplication also you see that this element is still in V. So you see that
It's
this
intact, yes.
closed under addition and scalar multiplication.
Ma'am, I have a small doubt, ma'am.
Yes.
Can't we consider as 1 plus 1 is 2 in the addition?
See, this
Yes,
is
ma'am.
what,
Same doubt.
see, here you see the symbol here. This symbol actually should have been given here as well. What does this symbol mean? Anyone knows? Here you see a dot and then equal to. What does that mean?
Such that equal to.
Such that.
No.
Equivalent.
Implies.
New definition. We are defining it in this way. We are defining it like this. This is not equal to this, but we are giving a new definition for this. I am going to call x comma 1 plus y comma 1 as x plus y comma 1. I am going to define it in this way. Okay. This is not the usual equal to. I am defining. This is a new definition I am giving.
So new definition after addition, right?
This for this addition itself, I am giving a new addition, a new definition. This definition is for this plus only. This plus is now taking a new definition.
Okay,
The
understood.
new definition is for
Okay.
plus one.
Ma'am, in the normal case, it will become x plus y comma 2, right, ma'am?
Exactly. But here I am defining it in a new way. Just like here it is defined in this new way. Here also I am defining it in a new way. Okay. Fine.
Yes,
we can define anything. We can define anything with this symbol, not 2 plus 2 equal to 5 also.
Yes. You can define it in your own way. So you can define it any way and see whether it will work for your scenario or not. Okay. Fine. Okay. So here you see scalar multiplication also. We are defining it. We are going to give a new definition for the scalar multiplication, which is this. And when I define it in this way, I see that this set is closed under addition and scalar multiplication. But if it is a usual addition and scalar multiplication, will this set be closed or not? Under addition and scalar multiplication?
No. Violated. The one extent one is violated.
Yes. But under this new definition, this set is now closed under addition and scalar multiplication. Now, what about the other properties? Maybe I will just do few properties.
Commutative property.
Maybe I'll just do few properties. You can do the remaining. So for example, maybe I'll do y comma 1 plus x comma 1. So now what is this? This is nothing but y plus x comma 1. So is it same as x comma 1 plus y comma 1?
Yes.
So
Yes, same.
first property is satisfied. What about the second one? The second one is associativity. So I am going to write x comma 1 plus y comma 1, add them up, and then I will add z comma 1. So it is x plus y comma 1 plus z comma 1, which is x plus y plus z comma 1. Now I am going to write x comma 1 separately, and I will first add y comma 1 with z comma 1, which will give me x comma 1 plus
Y comma z comma 1.
y plus z comma 1, which is x plus y plus z comma 1. So this property also you see both are equal.
Yes, ma'am.
Yeah. So it's associative. Yeah.
Yeah.
If y1 is in some negative value, then how it satisfies the commutative property?
If it is positive or negative, anyway you are just having this. See, what is you are asking? If I am having 2 minus 1 or minus 1 plus 2, What is the difference here? Nothing is changing, right?
Okay.
You're not changing the signs, just changing the positions. All right.
If you're taking XYZ, won't that go in the R3, ma'am? Because you are having three variables, right? Here.
There is only one comma in between. There are not more than two
Ma'am,
entries.
for associativity and commutative, we have to use same definition that defined earlier.
Yes, only one definition is there.
No, I mean just defined in the question, that's only definition we have to take for that also.
Yes. This is how you have to take for addition and scalar multiplication every time. Yes.
Okay.
Ma'am, sorry, can you please repeat for my doubt, ma'am? He interrupted in between, so I'm not able to follow what he said.
Sorry. Yeah. Continue.
So that X, Y, and Z, ma'am, that then it will come in R3 space, no, ma'am? It is still in R2.
See, what is R3? R3 means you should have three components in a vector. 1, 2, 3. Where all these components are real numbers. But here, X plus Y, Z, so all are like, you take any vector, only two components are there. It does not matter how many variables are inside each.
Okay, ma'am. Okay, got it. Okay.
Okay.
And
Yes.
ma'am,
Yes.
ma'am, what was that desperate need to define such operations in maths when to define the vector space we do such things?
Okay. See, I have had the same question when I studied also. I did not have chat GPT when I studied, but later on when I have Google and everything, I also just Googled to see why this kind of things are done. And then I saw that I have never seen any application straight away. So in higher mathematics, even though I have done PhD, I have not used this kind of strange operations for my research. But there are very huge applications. I forgot the topic. Actually, I even had one screenshot where I have just taken a picture from ChatGPT. What are the applications of this different type of operations? I have taken a screenshot. I don't know where I have saved it. Maybe I can post it to you later on. So there are some specific areas where this kind of things are really applied. Okay, that is why we are studying. Otherwise, what's the point of defining it so differently, right? So we are not studying the application right now, but there are definitely places where these are applied. Okay, so right now, sorry, I don't have the answer. I wanted to keep it with me, but somehow I don't know where I left it. Okay, fine. So
Okay, ma'am.
fine. Okay.
Ma'am,
Yes.
for every definition means for every axioms,
Mhm.
we define a new definition to prove this set is belong to vector space or not.
See,
Yeah.
at one time, you are going to consider one set with one particular definition and then check all the axioms. For each axiom, you cannot have different definitions. When you are considering one set at a time, you should consider one definition for all the axioms.
Okay, ma'am. Thank you.
Fine. Okay. So then what is the third one? What is the additive identity here? This is an interesting thing here. What is the additive identity here? So you have x comma 1. What is the element you add with this so that you see this element first of all should belong to this V. Remember that this is an element of V. This is an element of V. Don't forget that. And you should get back x comma 1. What is that element? Tell me.
0, comma
0,1.
So it should be
0,
a comma b should be 0 comma 1. So that is why what is mean by zero vector is different from origin. So that is why we don't say origin in many places. Instead, we say the zero vector. Zero vector. So now this is your zero vector. This is your additive identity. So here this zero does not mean origin, but it means the zero vector for this vector space with respect to this addition. Got it? So this is your additive identity in this case. You understand? The zero vector always does not mean just the origin. It depends on your vector addition and scalar multiplication.
So basically, it will vary from case to case, right?
Exactly. It depends completely on the way your addition and scalar multiplication are defined. Okay.
Ma'am, can you explain
Okay,
it one
comma
more
one
time for
Okay, fine.
actually not understand properly?
Okay, fine. I'll tell why this a comma b equal to 0 comma 1. This is what you want, right? Okay.
Yes, ma'am.
Okay. See, here what's happening is that first of all, your identity element should be a element of your set V. Okay, so this obviously means that the second entry should be 1. So your B is equal to 1 comes from the definition of your set.
Yes, ma'am.
Okay, and then for the first part, it is the usual addition only. So x plus a is equal to x means a should be 0. That's all.
Yeah.
Got it?
Got it. Thank you.
Okay, and then the next part here is you have what is the additive inverse. So let us say you are having again some entry here. Okay, x dash comma 1. You don't know what is your x dash, but here it is 1 that you know, and it should give you 0 comma 1. So what is your x dash?
Minus x.
Yes. So your additive inverse is minus x comma 1. Okay, so minus x comma 1 is your inverse of x comma 1. Okay, so I'm going we are just really running out of time, so I'm giving the remaining properties as a homework, which are quite simple to do, so I'm giving it as a homework. So these are the crucial part here. We did that, and the remaining are quite simple. I hope you can do that. Okay, fine. Okay, so we are moving to the next question. So far, are you with me? Yeah. Fine.
Yes, ma'am.
Yes, ma'am.
Okay, fine. Okay. Consider a set V is equal to set of all x comma y. So we are just considering R2 only here with usual addition in R2 and scalar multiplication defined like this. So in the previous case, the addition and scalar multiplication both were defined differently. So here in this case, the addition was defined differently and scalar multiplication was defined usually. So I'm just giving you different scenarios. So here addition is a usual addition, but scalar multiplication is defined in a different way like this now. Okay, so now I give you maybe 5 minutes. Consider the statements below, check which one is true. I give you 5 minutes, which I will take it as a break. So we'll continue again after 5 minutes, but you should all work on this and see which statement is true. All right.
Yes, ma'am.
Yes, ma'am.
Ma'am, can I say the answer?
Okay, so let's continue. Have you figured it out?
All properties are true, ma'am.
All properties are true.
Yes.
Okay.
Ma'am, I feel P, Q, and S are
And T
true.
are correct.
PQ and
PQ
S.
and S.
Only P, Q, and S.
Okay, so
PQ and S.
and
Yes,
then
sir. R and T. Yes, ma'am. R and T are not correct.
okay.
RS and this.
Let
Please explain, ma'am.
let us see.
Yeah.
Okay, one by one. So V is closed under addition. Obviously, it is true. Why? Because the addition is the usual addition, right? So there is nothing much to check. It is the usual addition, so it is closed. There is nothing much to check. We already have checked, so we know this is true. And V has a zero element with respect to addition. That also we know that because this is the usual addition. So here this is again true. This zero element is nothing but 0 comma 0. This also we know because of it is the usual addition. Now scalar multiplication is different. So whenever there is scalar multiplication, we have to be careful. Okay. So this statement R 1 dot V equal to V, we have to check. What is now V is equal to, we are going to check the statement R. Okay. So V is x comma y. Now what is 1 dot x comma y? According to this definition.
X by 2.
X by 2, comma y.
One. Right.
Y by
1.
1.
So C,
One.
yeah, that one, yeah.
Is this equal to x comma y?
No.
No.
No, right? This is not equal to x comma y. So it means what? 1 dot v is not equal to v. So this
Right.
statement is not correct. Okay. What about the property S? Let us look at property S. Now A times of, so let us say V1 is x1 comma y1 and V2 is x2 comma y2. Now V1 plus V2 is x1 plus x2 comma y1 plus y2. Now A dot A times of V1 plus V2 is equal to A times of x1 plus x2 comma y1 plus y2. Now according to the definition, let us assume that A is non-zero. So if A is non-zero, then we know that x1 plus x2 by
A.
2.
2.
and
A.
y.
Y1 by 2.
So there is a
A
A
also
also,
multiply, no?
right?
Then A will also be there, yeah.
So A times of x1 plus x2 by 2 and y by A.
Y1 plus Y2 by A.
Yeah.
Y1 plus Y2, no?
Y1 plus Y2, no?
Yeah. Y1 plus y2 by A. Right? Okay. Now what about the right hand side? You have AV1
Is not equal, yeah.
plus AV2. So what is AV1? AV1 is AX1 by 2 and Y1 by A.
Yeah.
And BV1, sorry, AV2 is
AV
BX1 by BX2 by 2 and Y2 by B.
B.
Right? Now what about the sum? AV1 plus AV2, it is AX1 plus BX2
Ma'am,
by
it will be AX2 by 2, right,
No,
ma'am?
it has to be A all the.
yeah.
All the
AX2 by 2, yeah.
That is A. Yeah. Here also A. So AX1 plus AX2 by 2 and comma Y1 by A, Y1 plus Y2
By A.
by A. So they are
Not
the same, right?
Right, ma'am.
They are the same.
same, yes.
Yes. So you see that LHS is equal to RHS. So it means your S is true. Correct? Okay. Now let us look at the next property.
Does not hold true.
So you have A plus B times of X comma Y. So this is A plus B times of X by 2 comma Y by A plus B. Assuming A plus B non-zero. Right? And what is AX plus BY? No. A times of XY plus B times of XY. So ax by 2 comma y by a plus bx by 2 comma y by b. Am I correct?
Ma'am,
Yes.
in case of A and B, we can also assume some constant and do it, right, ma'am? Scalar.
See, if you are proving something, you have to prove for any vector. For example, here it is proving. If you are disproving, you know that it is not correct, you can choose some specific scalars and do it. Yes.
Okay.
Okay. So here it is ax plus bx by 2 comma y by a plus y by b.
Not equal.
So you see that y by a plus b is not equal to y by a plus y by b. The first part coincides, but the second coordinate does not coincide. So you see that LHS is not equal to RHS. Okay, you understand why LHS is not equal to RHS, right? Because
Yes,
y
ma'am.
plus a plus b is not equal to y by a plus y by b.
One question, ma'am.
Here, this is the property we are checking. A plus b times of v is not equal to a times of v plus b times of v. Okay?
Ma'am, in option S.
Yes?
In option S, if we consider A to be 0,
Yes.
then the condition would false. No?
It has to be non-zero, no? It is
If
given.
A is 0, if A is 0, then everything is going to be 0. So anyway, it is going to hold, right?
Yes, ma'am.
Yeah. So for A equal to 0, it was trivial, so I just left it. But yeah, you have to check for that also. Okay, fine.
And I didn't got this R.
Sorry, you did not understand the R part.
Yes, ma'am.
R is the simplest one. See here, 1 dot V, how is it defined? 1 is your C now. Okay. So what is your C? Your C is nothing but 1. Okay. So now you apply it in your definition. It is a non-zero number. So this is the definition. C times of x, that is 1 times of x by 2. And then y by 1, y by C. So y by 1. So x by 2 comma y. So you have to check whether 1 times of v is equal to v or not. So here you obviously see it is not equal to v. Okay. Clear?
Yes, ma'am. Yes, ma'am. Got it. Got it. Yes, ma'am.
Okay. So I hope this problem is clear for everyone. Shall we move on?
Yes, ma'am.
Yes.
So there is this
Explain the next two as well, ma'am, please.
Okay. See, we are just doing the scalar multiplication definition. Whatever is given here, this scalar multiplication definition we are applying in each scenario. That's all. See, v1 and v2 are two vectors like this. This is the sum of the vectors. Now, what is a times of this v1 plus v2? So, according to the definition, now your a is nothing but your c. So in place of x, you have x1 plus x2, and in place of y, you have y1 plus y2, and in place of c, you are having a. That is all. Same is happening for these two also. You see that this is your LHS now, right? This is your LHS, a times of v1 plus v2, and your RHS is av1 plus av2. You see that both these expressions are exactly same, so it means your statement S is correct. But for T, what happens? Your LHS, you have y comma a plus b as your second element because your C is now a plus b. Okay. And for the RHS, your second coordinate is y by a plus y by b. And they are not equal. And so you see that LHS is not equal to RHS. That is a plus b times of v is not equal to av plus bv. So this statement is false. All right.
Okay. Thank you.
Okay. So cancellation law of vector addition, it is where the usual thing we do with the real number addition. So whenever there are common numbers, we simply strike it out, right? So the same thing can be done here also. If you have v1 plus v3 equal to v2 plus v3, then you can simply write v1 equal to v2. Okay. So this is cancellation law of vector addition. And what are the other important properties for vector space? We have already seen that the vector 0, that is the additive identity I am talking here. So this is the additive identity. So the additive identity is unique. Okay. Also, the additive inverse is also unique. What does it mean by unique? So there cannot be more than one element which can satisfy the property. Okay. So these elements are unique. Okay. So I don't want to get involved in too much with the proofs of these statements. It is enough as long as you know that it is unique. There cannot be more than one additive inverse and one additive identity. Okay.
Ma'am, what is the additive identity? I'm sorry.
See, additive identity means the element which satisfy the property that if you add that element to any vector, that will give you back the same vector. That element is the additive identity. Fine. Okay. Okay, so now moving on to subspaces. So we have seen what are the properties you need for vector spaces. Now we are going to look at what are subspaces. Obviously, the word sub means you can say that it is something which is sitting inside your vector space. So it is a subset first of all. Okay, so the vectors, each subspace is first of all a subset of the vector space. Okay, and if it is closed under addition and scalar multiplication, then we say that it is a subspace. Let me go slowly again. Okay, for example, maybe I will start with the example, very simple example. Let us say you are in R2. Okay, you are in R2. I guess we saw some example in the beginning. Maybe if it is there, then I can just pick that so it is easy. Yeah. So now, is this a subset of R2?
Yes, ma'am.
Right. So let us take the same set because we have already studied that set. So let us pick the same one for understanding. So let S be set of all x comma 0 such that x is in R. Now we know that this is first of all a subset of R2. Right. So the first thing, it is a subset of R2. So this is the first thing. What is the second thing? Is yes, closed under addition and scalar multiplication we have already verified. Yes or no?
Yes, ma'am.
So it is closed under addition and closed under scalar multiplication. Here you have to be careful. Whatever addition and scalar multiplication is defined for your original space V, the same operations only you should verify for your subset also. Then only you can consider it as a subspace of this space. Okay. So it means what? Suppose I'm considering the usual addition and scalar multiplication for V, then for S also I should consider the usual addition and scalar multiplication. I cannot use something different, maybe something like this. No. So whatever I'm considering for V, the same I should consider for S. Suppose I'm considering for V, for example, this kind of an operation, then for S also I should consider the same operation. Okay. You understand what I'm saying? Whatever operations are there you are using for V, the same operations only you should check when you are checking for the subset also. Okay, fine. So for a subspace, you don't have to check all the vector space axioms. It is sufficient if you just check this. First of all, it is a subspace and it is closed under addition and scalar multiplication. If you check this, then that is enough to say that S is a subspace of V.
Ma'am, if S is already then is a subset, then why do we need to check it for S also?
I'm checking it is a subspace, not subset. Okay. So
okay.
For a subspace, it should be first of all a subset and it should satisfy these conditions. Okay. So what are the conditions for a subspace? First of all, here it should be closed under addition. It should be closed under scalar multiplication. That's all. Okay. Fine. A subspace W of a vector space V is called a proper subspace if W is properly contained in V. You know what is proper, right? So it means what? It is not equal to V.
Every element.
All elements are present
there.
So proper means your W is not equal to V. That's all here. Okay. Fine. Okay. Every vector space V over R has two trivial subspaces. What are the trivial spaces? V itself is a subspace, of course, right? We can always consider the whole set as a subset of itself, right? So V itself is a subspace of V, and always the zero vector. Remember here, as I told you, zero vector means it need not be origin. You should understand zero vector means with respect to that addition and scalar multiplication. So this zero vector, if you just take the singleton set, then that is always
हेलो हेलो मैडम आप हो गए सिर्फ
Fast connection method. Yeah.
it up to 10 इसलिए क्या
sorry, my system got shut down. Sorry. So are you there with me?
Are you
So,
there? Yes, ma'am.
Yes, ma'am. Yes, ma'am. Very here.
okay. So let us continue. So yeah, so the trivial subspaces we saw are the subspace itself, the whole space itself, and the zero vector, right? So now
Ma'am,
let us.
it's your screen is not visible.
Oh, sorry. Okay, fine. Okay, so
Ma'am, could you repeat from a bit up?
so from here.
Yes, ma'am.
Okay. So what are the conditions? I have just wrote the conditions here. So the same conditions is repeated here. So first of all, your W should be a non-empty subset of V. Okay, that is the first thing. Okay, and then if it is closed, so the first condition here is, this is saying W1 W2 belong to V implies W1 plus W2 in V. So this is nothing but, what is this first condition? This is nothing but additive closure, right?
Yes, ma'am.
And the second condition is nothing but closure for scalar multiplication. So if these conditions are there, then we call W to be a subspace of V. So whatever I have said here, so here we are giving it in general terms. That's all. Okay. So what are the trivial subspaces for any vector space? The whole space and the zero space. The zero space is just the singleton set zero vector. Okay. Fine. Okay. So now we will look at some specific examples. So what is this W? W is the set of all x comma y such that x plus y is equal to 0. Right? So here you can rewrite it as set of all x comma minus x. Yes or no? Can I replace y with minus x? There is too much echo. Mute that. Okay. So just for easier computation purpose, I'm doing this. Okay. So x comma minus x, x is in R. So I'm just rewriting the set for easier computation purpose. Obviously, this is a subset of R2. Okay. So we just have to check closed under addition and closed under scalar multiplication. So is it closed under addition? I am taking x comma minus x, x1 comma minus x is one vector, and x2 comma minus x2 is another vector. Now let us add them up. What will I get? x1
x1 plus x2 minus times of x1 plus x2.
Yes. Okay. So you see that this sum belongs to W.
Yes, ma'am.
Also alpha times of x comma minus x is nothing but alpha x comma minus alpha x. So this also belongs to W. So W is a subspace of R2.
Eighth property we do not need to check, no? All those axioms.
For subspace, you don't need to check. For subspace, only these two are enough.
Okay.
But why you are taking minus x, ma'am? Even same thing can be done with y itself also, right? So why you are taking that as minus x? Y equal to minus x?
If see, it's just a matter of convenience only. So if you find this way to be convenient, you can of course do that. There is nothing wrong in that. Just I thought it is easier to complete it this way.
Okay.
Okay, so geometrically, what does this W represent? This is the line, right? Y is equal to minus x, right? Y is equal to minus x. This is the line, y is equal to minus x. So when x is equal to 1, your y is minus 1. When
Yes,
x is equal to minus 1, your y is 1. So y is equal to minus x, right? So this is a line which passes through origin. That is something very important you should note. This is a line which passes through origin. Okay. So from the above graph, it is clear that the line L passes through origin. Okay. So here something important is there. In general, a line in R2 is a subspace of R2 if and only if it passes through origin. Okay, I have underlined it in red. So first of all, can you tell me what is the equation of a line in R2?
Equal to mx plus c.
mx plus c.
Okay, so if c is not equal to 0, does the line pass through origin?
No.
Yes, ma'am.
Yes. Yes or no?
Yes, ma'am. Intercept will be no.
The line does not pass through origin, right?
Yes.
The line does not pass through origin. Okay, so then that line, then the line is not a subspace. Why it is not a subspace? Why it is not a subspace? If it does not
Zero
pass
element.
through origin,
Zero.
yes, 0 comma 0
Will
will
not
not be
will
there.
not satisfy the
So
equation of
it
the.
is not having the additive identity. So it cannot be a subspace, right? And also, if C is equal to 0, then sure, you know that it passed through origin. The line passed through origin. So this is for usual addition and multiplication only. So this condition is for usual addition and multiplication. I'm repeating. Okay. So then the line is a subspace.
Yes, ma'am. Right.
Okay? This is a very important thing you should all know. Okay. Fine.
Ma'am, could you once repeat this?
Ma'am, every line should be the subspace of R square, I think.
See, for example, if you recall, we in the beginning we saw the set of all x comma y such that x plus y is equal to 1. Do you remember?
Yes, ma'am.
So we saw that it is not closed under addition and scalar multiplication.
Okay.
Right? So you can see that you can rewrite it as y is equal to minus x plus 1. Y equal to mx plus c. Your c is 1 here. It is non-zero.
Yes, ma'am. Right.
Okay. It is not closed under addition and multiplication. So this is not a subspace.
Okay, I understood.
Okay.
No, ma'am, if we see graphically, then it can be.
Okay. I can show it graphically also. So what is your x plus y is equal to 1? So x plus y is equal to 1 means, so here if your x is equal to 1, your y should be
0.
0. So it is this point only, right? Same
Yes.
way if your y is equal to 1, your x should be
0.
0. So it means it is a line parallel to this, right?
Yes. Yes, ma'am.
Both intercepts are there.
So this is x plus y is equal to 1. Okay. Now,
Ma'am,
if it is
but
not passing through origin, it is not a subspace.
no, ma'am, that way true, but we can say it is in R square only.
It is a subset, but it is not a subspace. You understand?
Okay. Yes, ma'am. Okay.
Okay. Fine. Okay. So now look at this parabola. So now, is this parabola a subspace or not? Can you just say the
Subspace.
answer without like the technical verification, without the technical verification, conceptually, like with intuition, can you tell?
Yes, ma'am. 0, 0 belongs to this.
Yes, ma'am, it is.
What happens to scalar multiplication? What, see, the very first intuition is scalar multiplication means it should be along a line, right? Whatever you do scalar multiplication, the multiplied line will lie on a line, not along a curve. So suppose I am taking a vector, so for example it is passing through this point. Let us consider 1 comma 1. For example, I am going to consider the point 1 comma 1. All the scalar multiples should lie inside this set W for me, then only it is a subspace. Now y is equal to x is this line. Is this line inside this set W?
No.
No, right? 1 comma 1 belongs to W, but alpha times 1 comma 1 does not belong to W,
Yes, ma'am.
right?
Right.
So this is not a subspace.
Right, ma'am.
Okay, fine.
Can you explain again for scalar multiplication how it does not belongs to W?
See, what is alpha times of 1 comma 1? It is nothing but some point on this line, right? So apart from this 1 comma 1 and 0 comma 0, are there any other point which are in this line but also inside this set W? Suppose I am doing 2 comma 1 comma 2 times of 1 comma 1, 2 comma 2. So it is somewhere here. So does this point belong to this curve? Y is equal to x squared? No,
No.
right? So it means scalar multiplication is not closed under this set for this set. Okay.
So basically for any curve or any other graph function, so then we'll have to check with this function, right? Y equal to x, which is passing through the origin.
So this is just one simple scenario I can see. It is not necessarily y is equal to x. Here I just thought that this is a very easy thing to see. That's why I have taken this, but it is not the scenario that all the time you take y equal to x. No, no, no.
Okay.
Fine. So I just have taken a random example. If you want, you can just do it straight away. So you take alpha times of x comma y. Okay. So let's take x comma y belong to W. Y is equal to x square.
Square.
Right. So now what happens to alpha x comma alpha y? Now what is alpha x the whole square? Alpha square x square. Right. Now what your equation should satisfy? Alpha y should be equal to
Alpha x square.
alpha x alpha square
X square.
it should be alpha square x square only, right?
Yes, ma'am.
So what I'm missing here? What I'm missing here?
Ma'am, alpha y will be, ma'am, alpha square x square, right? Ma'am?
Your alpha y should be
Alpha x
yeah,
square.
your alpha y should be alpha square x square. But is it the case here? So you know that y is equal to x square. So alpha y is simply alpha x square, right? Yeah.
Yes, yes.
Okay, so that is why we see that here this is not the case. So alpha x squared is alpha square x square. But here y equal to x squared implies alpha y is alpha times x squared. So this and this are giving different things. So it does not belong to this set. Okay. So either you look with an example or you check straight away like this. Either way should work. Okay.
Ma'am, just a second, ma'am. So in this one, in alpha y, you got alpha square x square, or it should be alpha x square only, right, ma'am? The above where your cursor is there, basically. Just go up, ma'am. Yeah, alpha y equal to alpha x square below. This one.
So what you should actually get is that yes, alpha y is equal to alpha x squared only. Yes.
Yeah.
But here we should have alpha square x square for this to be inside this set. Okay, you understand or not?
Ma'am, sorry, ma'am. Can you please repeat that the one which I'm finally doing again, ma'am?
Yes, yes. See, alpha x comma alpha y. Okay, it is now suppose if it is in w, what it should satisfy? Alpha y should be equal to alpha x the whole squared.
Yeah.
If okay, if it is there in w, it should satisfy this condition, right?
Okay.
Alpha square x square. But what we have, but this is what we are having. We know that y is equal to x squared, which implies alpha y is equal to alpha x squared.
Correct.
I don't have alpha y is equal to alpha square.
Okay, got it.
Ma'am, but ma'am, in this one, like alpha y equal to alpha x, since you have written alpha y equal to alpha x whole square, okay, y equal to x, okay.
Okay, this is what we want, but this is what we have.
Okay.
So this is not a subspace. All right.
Okay.
Okay. Please mute. I'm getting echo. Okay. So this matrix example, maybe we will keep it for the next sessions. So we have some more examples here. So let us just stick to R2 today because we are almost running out of time. So only the examples, right? See, everyone, are you following the concepts? That is the important thing. So examples and all we can discuss in TA sessions. Problems and all is not a big thing. As long as you are clear with the concept, you can solve the problems. That is why I'm fine with giving more time to the concepts. So if you want to reduce the time, then I will not be able to solve all of your doubts. So I don't know how you prefer the sessions to go on. So is it okay that we do less problems and spend more time on the concepts?
Yes, ma'am.
Okay, the problems can be covered in the TA session. I will not leave the problems as it is. We can cover the problems in the TA sessions. All right?
Okay, ma'am.
Fine. Okay, so here, what are the subspaces of R2 in general? We saw that these are the trivial subspaces. This and this are the trivial subspace. Always this is trivial subspace is there for any vector space. So this is the trivial subspace of R2. Now what are the other subspaces of R2? Any line that passes through origin, that will form a subspace of R2. So if you consider any other line or you consider any other parabola or any other curve passing through origin also, these are all not subspaces. Okay, only the line through origin is a subspace apart from origin and entire plane. So for R2, everyone should have this in memory. Also you should have an understanding, but it should be there in the memory also, that what are the only non-trivial subspace of R2? Yes, what's the answer?
0, 0 in the entire plane origin.
Those are trivial, no?
Non-trivial means
Trivial.
Passing through origin.
origin. Okay.
Line passing through origin.
Line through origin.
Yes. So the equation you can have it in this way as well. X comma mx. Okay. Any set in this form. Okay. Any set in this form is a subspace of R2. Okay. So the zero subspace, line through origin, that is y is equal to mx, and the entire space. These are the subspaces of R2. Okay. So you have more subspaces, matrices and everything. So these are also very important, but in today's class, I guess we should wind up with this. We should not put too many things continuously. We are already ahead of time. So shall we wind it up now if you don't have any doubts?
Yes, ma'am.
Yes.
Okay. By the way, I wanted to ask about the attendance. Can you tell me any reason for the drop in the attendance?
Actually, today I think we have a instructor session for Python. That's why.
I see. Okay, fine. Actually, I was yesterday, because of Republic Day, I was told that I should not have sessions on public holiday.